Something is approaching us from the profound darkness of the outer edges. It is not moving quickly, nor is it flashy. It is simply inevitable. We know it by the name Bernardinelli Bernstein, a comet of such immense proportions that it renders every single interstellar guest we have previously observed into something resembling a tiny pebble. It spans 137 kilometers across, making it 10,000 times more massive than the object known as Oumuamua, or 3 Atlas. And it has been falling inward toward us for millions of years. Scientists claim that it acts as a time capsule from the very early days of our solar system, a frozen relic that carries deep secrets regarding our cosmic birth. However, others are asking some very uncomfortable questions. Why is it arriving precisely now? What was it that woke this giant up after billions of years of slumber? And what happens if we are not actually ready for what it might reveal to us? Do not go anywhere and remain with me, because by the time we reach the conclusion, you will fully comprehend exactly why this specific object alters absolutely everything. If you are as captivated by these cosmic enigmas as I am, go ahead and hit the like button and subscribe to the channel to stay in the loop as we track BB's long journey toward the inner solar system. Please leave a comment telling me where you are watching from, what hour it is in your corner of the world, and what your thoughts are on this new comet. Part 1. Why this object is not just big, it is wrong. Picture this scenario. You are an astronomer. You have spent your entire career studying comets. These are small, icy rocks that swing past the sun, light up for a few weeks, and then vanish back into the void. You know their sizes, and you know their behavior. You have cataloged thousands of them. And then, one day, you find something that makes absolutely no sense whatsoever. In the year 2014, buried deep in archival images from the Dark Energy Survey, astronomers spotted an object. At first, nobody paid much attention to it. Space is full of rocks, after all. But as they tracked it, measured it, and analyzed it, something became vividly clear. This was not just another comet. This was something fundamentally wrong. They designated it C2014 UN 271. Most people call it Bernardinelli Bernstein, or just BB for short. And BB is enormous. When the Hubble Space Telescope finally managed to get a good look at it, the measurements came back shocking. The nucleus alone might be 85 miles across. That is roughly 137 kilometers of solid, ancient ice and rock. To put that in perspective, most comets that we know are just a few kilometers wide. BB is not a comet in the traditional sense. It is more like a dwarf planet that decided to pretend it was a comet. It is roughly 10,000 times more massive than typical objects we have seen passing through, from interstellar space. Do you remember 3 Atlas, that tiny interstellar visitor that just zipped through our solar system? Atlas is small, fast, and fragile. It came from another star system entirely, moving at breakneck speed. BB is the opposite. It is colossal, slow, and stable. It has been part of our solar system for billions of years, lurking out in the Oort Cloud, that vast spherical shell of icy debris that surrounds our sun at unimaginable distances. And now, it is coming inward. Here is what makes BB truly bizarre. Comets are not supposed to be this big. Our models of the early solar system suggest that most comets formed from small clumps of ice and dust. They are rubble piles, essentially, loose collections of material held together by weak gravity. But BB is different. Its size suggests it formed differently, perhaps as a protoplanet that never quite made it. It is not a rubble pile. It is solid, structured, and that raises uncomfortable questions. Why does something this massive exist in the Oort Cloud? How did it get there? And why, after spending billions of years in frozen silence, is it suddenly active? Because here is the thing. BB started brightening years ago, way out beyond Neptune, where the warmth of the sun is barely a whisper. Water ice cannot sublimate at those distances. Water ice needs heat. But BB was glowing anyway. Something else was venting from its surface, something more volatile than water. In the year 2024, the Atacama Large Millimeter Array, known as ALMA, trained its radio eyes on BB. What they found was remarkable. Powerful jets of carbon monoxide, CO, were erupting from specific regions on the comet's surface. This was happening at around 16.6 astronomical units from the Sun. For reference, Saturn orbits at roughly 9.5 astronomical units. BB was way out there, and it was already active. Carbon monoxide sublimates at incredibly low temperatures, much lower than water. The fact that BB has enough CO to produce visible jets means it has massive internal reservoirs of this gas preserved for billions of years. Most comets do not have that. Most comets are depleted of hypervolatiles like CO by the time we see them, but not BB. BB is a time capsule. Mainstream astronomers love this. They call it a pristine sample from the early solar system, a relic from the era when planets were still forming. Study BB, they say, and you are studying the raw materials that built worlds, and they are probably right. But there is another question lurking beneath the surface. A question that makes some scientists uncomfortable. Why now? If BB has been sitting in the Oort Cloud for 4 billion years, undisturbed, why did it suddenly start falling inward? What changed? Was it purely random? Just cosmic chance? Or was there a trigger? Some theorists suggest galactic tides. Others propose a passing star. A few whisper about something else entirely, something unseen, something that nudged this giant awake and sent it tumbling toward the inner solar system. We will explore those possibilities soon, but for now, sit with this thought. An object the size of a small moon, filled with ancient gases, moving on a trajectory that defies easy explanation, is heading toward the sun. And we have no idea what really set it in motion. That is not just interesting, that is terrifying. Because if we do not understand what woke BB up, how can we predict what else might be coming? How many more giants are out there in the Oort Cloud waiting for the same mysterious push? And what happens if the next one is not heading for a safe perihelion near Saturn? What if the next one is heading straight for us? Hold that thought, because the mystery of BB's awakening is about to get stranger, much stranger. Part 2. The Awakening in the Dark. Why now? Imagine a bowling ball sitting on the edge of an ice rink. It has been there for 1 million years, motionless, perfectly balanced, and then, without warning, it starts to roll slowly at first, almost imperceptibly, but it is moving. The question is not whether it is moving. The question is what pushed it. That is the puzzle of BB. For billions of years, it sat in the Oort Cloud, that vast halo of frozen debris surrounding our solar system. The Oort Cloud extends from about 2,000 astronomical units to as far as 100,000 astronomical units or more. That is unimaginably distant. At those distances, the Sun is just a bright star among many. Gravitational forces are weak. Objects drift. They orbit the Sun on timescales of millions of years, and they are supposed to stay out there unless something disturbs them. So, what disturbed BB? One hypothesis involves galactic tides. Our solar system does not exist in isolation. We are part of the Milky Way galaxy, orbiting the galactic center. As we move through the galaxy, we encounter gravitational influences. the combined pull of countless stars, gas clouds, and dark matter creates tidal forces. These tides are not constant. They oscillate, they pulse. And some dynamicists believe these pulses can perturb cloud objects, nudging them inward. There is a specific model that has been circulating, a 14,400-year tide pulse scenario. The idea is that every 14,400 years or so, a particularly strong galactic tide sweeps through the outer Oort Cloud. Objects at the very edge, like BB, feel that tidal pull. Over time, their orbits change slowly, gradually, until one day they are no longer stable. They start falling inward. This model is speculative. It is not confirmed, but it fits some of the data. Then there is the passing star hypothesis. Our sun is not alone in space. Stars move. They pass near each other. Millions of years ago, another star might have drifted through the outer reaches of the Oort Cloud. The European Space Agency's Gaia mission has been mapping stellar motions across the galaxy. Some researchers have analyzed Gaia data and suggested that a star did pass near our solar system in the distant past, close enough to gravitationally perturb distant comets. A passing star does not need to get very close. Even at a distance of several thousand astronomical units, its gravity can tug on Oort Cloud objects. These tugs are small, incremental, but over millennia they add up. An object's orbit shifts, its eccentricity changes, and eventually it begins its long fall toward the inner solar system. If this is what happened to BB, then its awakening was not random. It was inevitable, a delayed consequence of an ancient encounter. But here is where it gets uncomfortable. If either of these scenarios is true, if galactic tides or passing stars are responsible, then we should expect more objects like BB, lots more. The Oort Cloud contains trillions of icy bodies. If tidal forces or stellar flybys can shake them loose, then BB is just the beginning. And that raises a question nobody wants to ask out loud. How many more are coming? Not all astronomers accept these models. Some argue that random diffusion is enough. Objects in the Oort Cloud naturally evolve over time. Their orbits slowly decay. No external trigger is needed, just patience. Billions of years of patience, and eventually some fall inward. It is cosmic roulette. BB's number came up, that is all. But there is a problem with that explanation. It feels too convenient, too clean. Because BB is not just any comet. It is massive, it is unusually structured, and its timing, arriving in our observational era, in the age of advanced telescopes, feels almost orchestrated, almost like something wanted us to see it. That is where the whispers start. The quiet speculation, the uncomfortable theories. If not galactic tides, if not a passing star, then what? Could there be something else out there? A hidden planet? A dark matter clump? Something we have not detected yet? Something that has been quietly perturbing Oort Cloud objects for eons. There is a story. A researcher, someone respected in the field, once told colleagues over drinks, "I do not believe in hidden planets, I really do not. But something huge must have disturbed that object. The math does not work otherwise, the odds are too low. And when the math does not work, either your assumptions are wrong, or there is something you are not seeing. So which is it? Are our assumptions wrong? Or is there something out there we are not seeing? And if there is, why can we not find it? Why does it remain hidden? Is it simply too faint, too far, too small to detect? Or is it something stranger? Something our instruments are not designed to recognize? We will explore those possibilities soon. But first, we need to understand BB's orbit because its trajectory holds clues. Big, unsettling clues. And those clues suggest that whatever woke BB up, it did not just give it a gentle nudge, it fundamentally altered the geometry of its path through space. And that geometry is deeply, profoundly weird. Part 3. The perpendicular orbit nobody expected and why it matters. Orbits tell stories. If you know how to read them, they reveal where an object came from, what forces shaped it, and where it is going. Most objects in our solar system orbit in roughly the same plane. The planets, asteroids, most comets, they all circle the sun in a relatively flat disk called the ecliptic. This makes sense. The solar system formed from a rotating disk of gas and dust. Everything inherited that rotation. Everything orbits in the same general direction at similar angles except BB. BB's orbit is tilted at about 95.5 degrees relative to the ecliptic. That is nearly perpendicular. Imagine the planets orbiting the sun like runners on a track. BB is not on the track. It is coming in from above, cutting straight down through the plane. That is bizarre. That is not how comets are supposed to behave. Why does this matter? Because inclination tells you about an object's dynamical history. Low inclination orbits suggest an object formed in the protoplanetary disk and stayed there. High inclination orbits suggest something violent happened, a gravitational interaction, a close encounter, something that kicked the object out of the plane. And near perpendicular orbits, those suggest chaos, deep, ancient chaos. One explanation is the deep Oort chaos model. The Oort cloud is not uniform. It is not a calm, orderly shell of ice. It is dynamically hot. Objects out there move in all directions at all inclinations. They have been jostled by passing stars, galactic tides, and planetary perturbations over billions of years. By now, the Oort cloud is a chaotic mess. Objects orbit every which way. So maybe BB's perpendicular orbit is not unusual. Maybe it is just a product of that chaos. But there is another idea, a more controversial one. What if BB is not originally from our solar system at all? What if it is a captured interstellar object? Billions of years ago, during the early days of the solar system, stars were closer together. Planetary systems were still forming. Objects drifted between stars. Some got captured, trapped in another star's gravity well, stuck in the Oort cloud, waiting. If BB is a captured interstellar object, that would explain its weird orbit. It came from somewhere else. Its inclination reflects its origin, not ours. And now, after billions of years in exile, it is finally falling inward. This theory is speculative. There is no direct evidence, but it fits. Compare BB to 3 Atlas. Atlas came through on a hyperbolic trajectory. It entered the solar system, swung past the sun, and left, never to return. It was clearly interstellar. But BB is bound to the sun. It is on an elliptical orbit. It will swing inward, reach perihelion, then head back out. It is not leaving. It belongs here, or at least it has been here long enough to belong. Orbital mechanics are unforgiving. BB's inclination affects everything: how it interacts with the giant planets, how solar radiation heats its surface, and how outgassing jets behave. As it moves inward, it will cross the orbital planes of Saturn, Jupiter, maybe even the inner planets. Each crossing is a potential gravitational encounter, a chance for its orbit to change. There is a concept in celestial mechanics called orbital resonance. When two objects have orbital periods that are simple ratios of each other, they can influence each other profoundly over time. Jupiter and Saturn are in near resonance. Their gravitational dance shapes the entire outer solar system. Could BB enter a resonance with one of the giant planets? Could that change its path, make it more dangerous, More unpredictable? It is possible, unlikely, but possible. And that uncertainty bothers astronomers because we like predictability. We like knowing where things are going. But BB's orbit, with its steep inclination and uncertain perturbations, introduces chaos. And chaos is hard to model, hard to predict, and hard to prepare for. Some theorists find the inclination unsettling for another reason. They argue it feels engineered, not naturally evolved, as if something deliberately placed BB on this trajectory. That is fringe thinking. Most scientists dismiss it, but the feeling persists. The orbit is just too specific, too unusual, too unlikely. Could a phantom planet have pumped BB into this orbit? Could an unseen massive body lurking beyond Neptune have gravitationally sculpted BB's path over millions of years? We will explore that idea soon. But for now, consider this. An object's orbit is its fingerprint. It tells you its history, and BB's orbit tells a strange, uncomfortable story. A story of forces we do not fully understand. A story of something somewhere exerting influence we cannot quite see. And if we cannot understand BB's orbit, how can we understand what is inside it? How can we predict what it will do as it gets closer to the sun? Because what is happening on the surface, those jets of carbon monoxide, those bursts of light, they are just symptoms. The real mystery is inside that massive nucleus, inside the structure of the object itself. And recent observations are giving us our first tantalizing glimpses of what BB really is, and it is not what we expected. Part 4. Internal structure. The monster made of layers. Comets do not like to give up their secrets. You can watch them from Earth. You can send spacecraft to fly past them. But understanding their internal structure, that is hard. Really hard, because you cannot crack one open. You cannot drill into it. You have to infer. You have to deduce from limited data. And in the case of BB, that data is both fascinating and deeply puzzling. The Hubble Space Telescope has been watching BB for years now. Hubble is good at imaging. Really good. And what Hubble saw surprised everyone. BB's nucleus is not jagged. It is not an irregular rubble pile like most comets. It is nearly spherical, smooth, and uniform. That suggests something important. It suggests internal forces shaped this object. Gravity, perhaps, or thermal processes. Something that molded it into a sphere over billions of years. Spherical objects in space usually fall into two categories: planets and moons held together by strong gravity, or differentiated bodies where heavier materials sink to the center and lighter materials rise to the surface. BB is too small to be a planet, but it might be differentiated. It might have layers, an outer crust, a mantle of different ices, maybe even a core of rock and metal. That would make it more like a miniature planet than a comet. ALMA, the radio telescope array in Chile, added another piece to the puzzle. In 2024, ALMA mapped carbon monoxide jets erupting from BB's surface. These were not random bursts. They were organized, emerging from specific regions, persistent over time. That tells us something crucial. The interior is not uniform. There are pockets of volatiles, reservoirs of CO trapped beneath the surface. And as BB moves closer to the sun, those reservoirs heat up. The pressure builds, and eventually the gas escapes. Carbon monoxide is a hypervolatile. It sublimates at incredibly low temperatures, much lower than water. The fact that BB has enough CO to produce visible jets at 16 astronomical units means its interior is loaded with this stuff. Most comets lose their CO quickly. It vents away early in their lives, but not BB. BB has been cold enough for long enough to preserve massive amounts of CO deep inside. That is extraordinary. Here is where it gets speculative. Some researchers propose a stratified chemistry model. Imagine BB like an onion, layers upon layers. The outermost layer is a crust of silicates and refractory materials. Beneath that, a layer of water ice mixed with organics. Deeper still, carbon dioxide ice. And at the core, perhaps pockets of pure CO. Each layer formed at different temperatures during the solar system's early days, each layer preserved by the freezing cold of the Oort Cloud. As BB approaches the Sun, these layers heat up sequentially. First, the outermost crust warms, then water ice starts to sublimate, then carbon dioxide, then CO. Each phase produces different outgassing behavior, different jets, different brightness. And what we are seeing now at 16 astronomical units is just the beginning. The CO layer is starting to vent, but the deeper layers are still frozen, still waiting. There is another idea floating around: phase-trapped hypervolatiles. This is the notion that certain volatile compounds can exist in unusual crystalline structures at very low temperatures. Structures that trap gases inside, and those structures only break down when warmed to specific temperatures. So maybe BB has been sitting out there with CO locked inside weird ice crystals. And now, as it warms, those crystals are breaking. The CO is escaping, and that is driving the activity we see. This has mechanical implications. Internal pressure from trapped gases can fracture the crust, create cracks, fissures, and those fissures become vents, jets. Over time, as more gas escapes, the structure weakens, fragments break off. The comet changes shape. Some comets fragment dramatically when they get close to the Sun. Will BB? Nobody knows, but the possibility is there. What we do know is that BB is not behaving like a typical small comet. Small comets have erratic jets, random bursts of activity. But BB's jets are organized, powerful, and persistent. That suggests an internal engine, a system of vents and reservoirs working in concert. And that is not typical. That is weird. That is the kind of behavior you would expect from a cryovolcanic world. A small icy moon with internal heat, not a comet. So what is BB really? Is it a comet? Is it a dwarf planet? Is it something in between? And does it matter? Well, yes, it matters a lot, because how we classify BB determines how we study it, what questions we ask, what missions we propose, and what dangers we prepare for. Because if BB is more planet-like than comet-like, then its behavior near perihelion could be radically different, more violent, more unpredictable, more spectacular. But we are getting ahead of ourselves because before we can plan how to study BB up close, we need to understand its timeline. How long do we have? When will it get close? And what does that mean for our observation window? Because here is the uncomfortable truth. BB is moving slowly, majestically, like a skyscraper drifting through space. But that slowness is deceptive. Because time is running out, the window to study this object, to really understand it before it changes forever, is narrower than you think. Part 5. A slow-motion approach, but a fast-moving mystery. Imagine a skyscraper made of dirty ice, not a metaphor. Literally a building-sized structure, frozen solid, coated in ancient organics, drifting through the void. That is BB, and it is coming slowly, inexorably, heading inward toward the Sun. But here is the paradox. Even though it is moving slowly, there is urgency, because every year that passes, BB changes. And once it changes too much, we lose our chance to study what it really was. BB was first spotted in archival images from the Dark Energy Survey in 2014. but it was not identified as unusual until later. By the time astronomers realized what they were looking at, BB had already been moving inward for years, maybe decades, maybe centuries. Its orbit suggests it started falling from the Oort Cloud long before humans invented telescopes. We just happen to notice it now. Right now, BB is still far from the Sun, beyond Neptune, moving slowly through the outer solar system. Its current distance fluctuates as it orbits, but during recent observations, it was around 16 to 18 astronomical units out. For context, Neptune orbits at about 30 astronomical units, Saturn at 9.5, Jupiter at 5. BB is still in the outer neighborhood, but it is heading inward, and we know where it is going. Astronomers have calculated BB's trajectory with high precision. It will reach perihelion, its closest approach to the Sun, in January of 2031. And perihelion will be at about 10.9 astronomical units, just beyond Saturn's orbit. Not close by any means. BB will not threaten Earth. It will not come anywhere near the inner planets, but 10.9 astronomical units is close enough for solar heating to change everything. Here is the window. Between now and 2028, maybe 2029, BB will undergo its most dramatic transformation. Right now, it is venting CO, subtle jets, gentle outgassing. But as it gets closer, water ice will start to sublimate. The coma, that fuzzy cloud of gas and dust around the nucleus, will thicken. Jets will intensify. The comet will brighten. And all of that activity will make it harder to study the nucleus itself, harder to see what is really happening beneath the surface. So the most valuable observations need to happen now, in the next few years, before BB gets too active, before the coma obscures everything. Scientists are scrambling, Hubble is watching, ALMA is listening, ground-based telescopes are tracking, large optical surveys are capturing data. Every observation adds a piece to the puzzle. Every spectrum reveals a new molecule. Every image shows subtle changes. But there is never enough time, never enough data, never enough certainty. There is another risk: fragmentation. Some comets do not survive their close approach to the Sun. They break apart, disintegrate under thermal stress and rotational forces. If BB fragments, that is both a disaster and an opportunity. A disaster because we lose the intact object. We lose the pristine interior, but an opportunity because fragmentation exposes fresh material, interior ices that have never seen sunlight. And that material could tell us everything. Will BB fragment? Nobody knows. Its size suggests stability. Large objects are held together by stronger gravity. They are less likely to break apart, but internal pressure from outgassing could weaken the structure, create faults. And if BB has a layered interior, like we suspect, those layers might separate under stress. Imagine peeling an onion layer by layer, each fragment revealing a different epoch of solar system history. Even if BB does not fragment, its appearance will change dramatically. Right now, it is a faint smudge, visible only to large telescopes. But by 2030, 2031, it could be bright enough to see with amateur equipment. Not the naked eye, but a decent telescope could spot it. Imagine that. A comet the size of a small moon glowing in the outer solar system, visible to anyone with the patience to look. That is rare, that is special, but it is also temporary. After perihelion, BB will swing back outward. It will fade, cool down, and retreat into the darkness. Its orbital period is millions of years. Once it leaves, it will not be back. Not in our lifetimes, not in our civilization's lifetime. This is a once-in-a-species opportunity, a chance to study an object that has existed unchanged since the solar system was young, and we are living through it right now. So the urgency is real. Scientists are pushing for more telescope time, more observations, more data. Some are even proposing missions, crazy, ambitious missions to send a probe to BB, to fly past it, to study it up close. Most of those proposals are pipe dreams. The engineering is too hard. The funding is not there, but the desire is real. Because we know what is at stake. We know what we will lose if we do not act. And here is the haunting part. We are not just watching a comet. We are watching something ancient and vast awaken. Something that has slept in the cold dark for billions of years. And now, for reasons we do not fully understand, it is waking up, moving, changing, heading toward the sun. And we may never fully understand why. We may never know what set it in motion, what forces, what events, what invisible hands guided this giant out of the shadows and into our view. But it is here now, and it is watching us as much as we are watching it. And that thought, that uncomfortable existential thought, should keep us all awake at night. Part 6. What if it is not alone? The clustering problem. Patterns matter. In science, in nature, in the cosmos. Patterns tell you something is happening, something real, something that demands explanation. And right now, there is a pattern emerging in our solar system that is making astronomers very uncomfortable because over the last decade, we have detected a cluster of unusual objects entering or passing through our neighborhood. And the odds of that being random are disturbingly low. Let us rewind. October 2017, astronomers spot Oumuamua, the first confirmed interstellar object ever detected passing through our solar system. It is small, elongated, tumbling. It does not behave like a comet. No visible coma, no jets, but its trajectory bends slightly as it passes the sun, suggesting some kind of outgassing. Scientists argue for months about what it is. Asteroid? Comet? Something else? To this day, nobody knows for sure, but one thing is certain. It came from another star. It passed through and it left. August 2019, Borisov arrives. Another interstellar object. But this one is clearly a comet. Visible coma, gas jets, spectroscopy reveals familiar molecules. Carbon monoxide, water, cyanogen. Borisov behaves like comets from our own solar system. That is reassuring. It suggests comet chemistry is universal. But it also raises a question. If interstellar comets are common, why did we only start seeing them in 2017? 2025, 3 Atlas shows up. Small, fast, interstellar, barely studied before it leaves. And now we have BB, not interstellar, but massive, ancient, anomalous. 4 unusual objects in less than a decade. Is that normal, or is something happening? The observational bias argument says yes, it is normal. Our telescopes are better now. Surveys are more comprehensive. We are scanning more sky more often with better sensitivity. Of course, we are finding more objects. We are looking harder, that is all. Nothing mysterious about it. Just better technology revealing what was always there. But some dynamicists are not convinced. They have run the numbers. They have calculated the expected rate of interstellar object encounters based on stellar densities, velocity distributions, and gravitational cross-sections. And the numbers do not quite add up. We are seeing more than we should. Not by a huge margin, but enough to notice, enough to wonder. If the cluster is real, if it is not just observational bias, then something is happening. And the most likely explanation involves the Oort Cloud, because the Oort Cloud is vast, enormous. It contains trillions of icy bodies. And it is not static, it is dynamic. Objects move, drift, get perturbed. And if something is perturbing them more than usual, if some external force is shaking the cloud, then we would expect more objects to fall inward, more comets, more anomalies, more surprises. This leads to the trans-Oort perturber hypothesis, the idea that something massive, something we have not detected yet, exists beyond the Oort cloud and is gravitationally stirring things up. Not Planet 9, not necessarily, but something. Maybe a substellar object, a brown dwarf that passed through the outer solar system millions of years ago, or maybe a dense clump of dark matter, or maybe something we have not even conceived of yet. The hypothesis is speculative. There is no direct evidence, but it is tantalizing because it explains the cluster. It explains why BB and other objects are arriving now. It suggests an external trigger, an event in the recent past, astronomically speaking, that disturbed the Oort cloud and set multiple objects on inward trajectories. And if that is true, then BB is not alone. There are others already on their way. Objects we have not detected yet. Giants lurking in the dark, slowly falling toward the inner solar system. Critics caution restraint. Selection effects are powerful. Telescopes are biased toward finding unusual objects because unusual objects are interesting. Funding goes to surveys that discover weird things. Careers are built on anomalies. So maybe we are over-interpreting. Maybe the cluster is an artifact of human curiosity, not cosmic reality. Maybe there is nothing unusual happening at all. But there is a story. A researcher who ran simulations, thousands of them, modeling Oort Cloud dynamics under various conditions. And the code kept failing to produce the observed cluster. Not unless they added something else. An external perturber, a hidden mass, something that was not supposed to be there. And when they added it, the simulations matched reality. The cluster appeared. The objects fell inward. The timing worked. And the researcher quietly, reluctantly told colleagues, "I do not know what it is, but something is out there." So, what is it? What could perturb the Oort cloud on this scale? A rogue planet? A dark matter structure? Something even stranger? And if it exists, why have we not found it? Why does it remain hidden? Because if there is one thing scientists hate, it is invisible forces. Invisible forces feel like magic. And science is not supposed to need magic. Science is supposed to explain things. But right now, we do not have an explanation. We have a cluster, a pattern, and a growing suspicion that the outer solar system is hiding something big. And speaking of hidden things, there is one candidate that keeps coming up in conversations. One ghost that refuses to die, one hypothesis that explains so much yet remains frustratingly elusive. It is called Planet 9, and it might be the key to understanding everything. Part 7. The Planet 9. Ghost, a threat, a myth, or a convenient placeholder. Ghost stories are compelling because they are unfalsifiable. You cannot prove a ghost does not exist. You can only fail to find it. And Planet 9 is the ultimate ghost story of modern astronomy. A massive planet, 5 to 10 Earth masses, lurking in the outer solar system, far beyond Neptune. Too faint to see, too distant to detect. But maybe, just maybe, real. The hypothesis emerged in 2016. Astronomers noticed that several trans-Neptunian objects, TNOs, had unusually aligned orbits. Their perihelia, the points where they come closest to the Sun, clustered in the same region of space. That is weird. Random orbits should not align like that unless something is shepherding them. Something massive, something with enough gravity to corral distant objects into similar paths. So they proposed Planet 9, a super-Earth ejected from the inner solar system during the early chaotic period when planets were still forming. It got kicked outward by Jupiter, or Saturn, settled into a distant eccentric orbit, and it has been out there ever since, invisible, silent, but gravitationally active, slowly sculpting the orbits of TNOs over millions of years. The hypothesis is elegant. It explains the orbital clustering. It explains some of the weird inclinations. It even predicts where Planet 9 should be. Roughly, sort of. The problem is nobody can find it. Surveys scan the predicted region. Nothing. Deep imaging campaigns? Nothing. Infrared searches? Nothing. If Planet 9 exists, it is either fainter than expected, or in a different location, or both. And that is where things get murky, because in 2024 and 2025, new papers started, circulating. Some supported Planet 9. Others proposed alternatives, and a few suggested that the whole thing might be a statistical fluke. One alternative is the self-gravitating disk instability model. Instead of a single planet, imagine the outer solar system contains a disk of small bodies, thousands of them. And this disk has enough total mass to gravitationally interact with itself. Clumps form. Those clumps perturb other objects, and over time, you get orbital clustering without needing a single massive perturber. It is collective gravity, emergent structure. No Planet 9 required. Another alternative is the phantom perturber. Not a physical object at all, just a gravitational signature. Maybe it is dark matter. Maybe it is a transient structure that passed through the outer solar system millions of years ago and is now gone. Maybe it is an artifact of how we model gravity at extreme distances. The math works. The observations fit. But there is nothing actually there. Here is why this matters for BB. If Planet 9 exists, or if some massive perturber exists, it could have nudged BB inward. It could have destabilized BB's orbit millions of years ago, setting it on a collision course with the inner solar system. And if that is true, then BB is not a random comet. It is a victim, an object pushed by unseen forces, and those same forces could be pushing others. But what if Planet 9 does not exist? What if the orbital clustering is just noise? What if we are seeing patterns where none exist? Then BB's journey is random, chance, cosmic roulette. And that is almost scarier because randomness means unpredictability. It means we cannot forecast what is coming. We cannot prepare. We can only watch and hope. Some researchers argue the Planet 9 signal could be a statistical fluke. Surveys are biased. They focus on certain regions of the sky. Bright objects get noticed. Faint objects do not. And when you correct for those biases, the orbital clustering might disappear. The whole hypothesis collapses. Planet 9 becomes a mathematical ghost, a convenient placeholder for our ignorance. But then there are the true believers, the astronomers who have spent years searching, who have refined their models, who have mapped every possible hiding spot, and they are not giving up. Because even if Planet 9 is not where they expected, even if it is fainter or smaller or on a different orbit, the gravitational effects are real. Something is out there. Something has to be. And then there is the truly speculative stuff. The ideas that make mainstream astronomers uncomfortable. What if Planet 9 is not a planet at all? What if it is a primordial black hole, a tiny one formed in the first fraction of a second after the Big Bang, mass equivalent to 5 Earths, but compressed into an object the size of a grapefruit? It would have the right gravitational signature. It would explain why we cannot see it. And it would be utterly bizarre. Or maybe it is a dense knot of dark matter. Dark matter clumps on large scales. We know that. But could it clump on small scales too? Could there be a dark matter concentration in the outer solar system? Massive enough to perturb orbits but invisible to every telescope we have. Some physicists say yes. Others say no. Nobody knows for sure. There is a story about an astronomer who once joked, If I find Planet 9, I will name it after my dog, but I might never find it because the outer solar system is vast. Really vast. And searching for a faint object in that much space is like searching for a needle in a haystack the size of a continent. You could search for decades and miss it by a few degrees, or it could be right there hiding in plain sight, and you would never know. But here is the existential question. Does it matter? Does it matter if Planet 9 is a planet, a black hole, a dark matter clump, or nothing at all? Because regardless of what is out there, the effects are real. Objects are being perturbed. BB is falling inward. The clustering is happening. And something somewhere is pulling strings. And that something could tell us profound things about how the solar system works, about what forces shape planetary systems, about what is possible in the universe. And maybe, just maybe, BB is not even a comet. Maybe it is something else entirely. Something that challenges our definitions. Something that sits on the boundary between comet and planet, between natural and unnatural, between expected and impossible. Because the more we learn about BB, the more it feels wrong. Not just unusual, wrong, like it doesn't quite belong in the categories we have built. And that raises the most uncomfortable question of all. What exactly is BB? Part 8. When a comet is too big, the dwarf planet hypothesis. Definitions matter in astronomy. They are not just semantic. They shape how we think about objects, how we study them, how we classify them. And right now, BB is breaking the definitions. Because by every traditional measure, BB is a comet. It has a coma, it has jets, it is venting gas. But by size, by structure, by composition, it is something else. It might be a dwarf planet. And if that is true, then everything changes. Let us start with the evidence. Size. BB's nucleus is roughly 85 miles, 137 kilometers across. That is enormous for a comet. Typical comets are a few kilometers, maybe 10 at most, but 85, that is in dwarf planet territory. Pluto's moon, Charon, is around 1,200 kilometers. Ceres, the largest object in the asteroid belt, is about 950 kilometers. BB is smaller, yes, but it is in the same ballpark. It is not a tiny ice ball. It is a world. Then there is shape. Hubble images show BB is nearly spherical. That is important. Small objects held together by weak gravity are irregular, lumpy, but large objects with stronger gravity pull themselves into spheres. It is called hydrostatic equilibrium, and it is one of the criteria for being a planet or dwarf planet. BB has it. That suggests significant self-gravity. That suggests internal pressure. That suggests it is more than just a rubble pile. Now consider composition. ALMA detected carbon monoxide jets. Powerful ones, persistent ones. That means BB has massive internal reservoirs of CO. Most comets lose their CO early. It vents away because it is so volatile. But BB has held on to it for billions of years. That requires a specific structure, layering, maybe even differentiation. Heavier materials sinking to the center, lighter materials rising to the surface, just like a planet. Some scientists are proposing a cryovolcanic preconditioning model. The idea is that BB, over billions of years, experienced internal heating not from the sun, from radioactive decay. Elements like aluminum-26, potassium-40, uranium. These decay. They release heat. And in a large enough object, that heat can build up, warm the interior, create liquid pockets, cracks, pathways for gas to escape. Imagine it like this. BB formed in the early solar system. It was a protoplanet, a building block for something larger. But it got ejected before it could finish growing, kicked out to the Oort Cloud, frozen solid. But inside, radioactive decay continued slowly over billions of years, warming the core, fracturing the crust, building pressure. And now, as BB moves inward and solar heating adds to that internal warmth, the pressure is releasing. The gas is venting. The jets we see are not just sublimation. They are cryovolcanic eruptions, mini-volcanoes of frozen gas. If this is true, if BB is a proto-dwarf planet with internal heat, then studying it becomes incredibly valuable because we have never seen an object like this up close. We have studied comets. We have studied dwarf planets, but we have never studied something in between, something that is transitioning, something that is waking up after billions of years of dormancy. What would that look like near perihelion? Cryovolcanic eruptions, dramatic jets, massive outgassing, maybe even surface changes, fractures opening, chunks breaking off, temporary atmospheres forming and dissipating. It would be spectacular, a once-in-a-lifetime event, and we would have front-row seats. But here is the problem. If BB is more planet-like than comet-like, then missions to study it become even more important and even more difficult. Because dwarf planets are complex, they have geology, internal structure, active processes. You cannot understand them from a distance. You need to get close, land on them, drill into them, and that is nearly impossible with current technology. Not everyone accepts the dwarf planet hypothesis. Critics point out that BB's activity is consistent with normal comet behavior, just scaled up, bigger object, bigger jets. Nothing exotic required. No internal heat, no cryovolcanism, just a lot of CO sublimating as it approaches the sun. Occam's razor. The simplest explanation is usually right, but there is a middle ground, the hybrid object concept. Maybe BB is transitional, not fully comet, not fully dwarf planet, something in between, an evolutionary link, a snapshot of how small icy worlds grow and change. And studying it could tell us how Pluto formed, how Eris formed, how all the dwarf planets in the outer solar system came to be. There is a story. A planetary scientist, after reviewing Hubble data and ALMA observations, remarked to a colleague, "If this thing is a dwarf planet, then we just discovered a missing link in the family tree of the solar system, and we did not even know we were looking for it." That is the beauty and frustration of astronomy. Sometimes you find things you were not searching for, and those things change everything. So, what is BB? Comet, dwarf planet, hybrid. Does it matter? Yes, because classification determines study. It determines funding, it determines missions, and it determines how we think about the outer solar system. If BB is unique, then it is a curiosity, interesting but isolated. But if BB represents a class of objects, if there are more proto-dwarf planets lurking in the Oort Cloud, then the outer solar system is far more complex than we thought, far more active, far more dangerous. And that brings us to the whispers, the speculation, the uncomfortable theories that float around in private conversations, because some people, not many, but some, are asking a bolder question. What if BB is not natural at all? What if it is something else? Something artificial? And before you dismiss that as absurd, let us examine why people are even asking. Part 9. The Artificial Body. Whisper Network. Conspiracy theories start in the gaps, in the places where data is sparse and explanations are weak. And right now, BB has gaps, big ones. Its brightness is unusually stable. Its jets emerge from the same regions persistently. Its orbit is weirdly specific. And when scientists cannot fully explain something, other people fill in the blanks, sometimes with wild speculation, sometimes with uncomfortable questions, and sometimes, rarely, with ideas that turn out to be right. Let us be clear, There is no evidence that BB is artificial. None. Zero. But there is a whisper network, forums, blogs, think pieces, people pointing at anomalies and asking what if. So let us address it. Not because it is likely, but because ignoring fringe theories does not make them go away. It makes them fester. So let us engage rationally and see what holds up. First claim, BB's light curve is unusually stable. Most comets fluctuate. They brighten and fade erratically as they rotate and vent gas. But BB's brightness changes are smooth, predictable, almost too regular. Some argue that suggests structural stability, like a rigid object, not a loose rubble pile. And if it is rigid, if it is engineered, maybe that explains the stability. Counterpoint. Large objects rotate more slowly. They have more inertia. Their light curves naturally smooth out. And BB is large, so stable brightness is not suspicious. It is expected. No artificial structure needed. Second claim, the jets. ALMA mapped CO jets emerging from specific regions on BB's surface, and those regions seem to vent persistently, always the same spots. Some people argue that feels designed like vents on a spacecraft, controlled, deliberate. Counterpoint. Cometary jets often emerge from specific regions called active areas. These are places where the surface is fractured or where subsurface ice is exposed. Once established, these vents can remain active for years. It is geology, not engineering. Natural processes create persistent features all the time. Third claim, the orbit. 95 degrees inclination, nearly perpendicular to the ecliptic. Some argue that feels placed like something deliberately put on that trajectory. Why would a natural object have such a specific orbit? Counterpoint. High inclination orbits are common in the Oort Cloud. Dynamical interactions, galactic tides, passing stars, all these sculpt orbits over billions of years. Perpendicular inclinations are not common, but they are not impossible. And one unusual orbit does not mean artificial origin. It means unusual history. So, scientifically, the artificial hypothesis falls apart. But let us go further. Let us speculate. What if BB were artificial? What would that even mean? What could it be? A probe? Some suggest BB could be an alien probe sent by an advanced civilization to study our solar system, disguised as a comet to avoid detection, moving slowly to gather data over long time scales. It is a romantic idea, but it raises questions. Why disguise it? Why not communicate? Why wait billions of years? And how would you even build something that large? A storage facility. Another idea, maybe BB is a data vault, a cosmic hard drive built by a civilization that wanted to preserve information across deep time. They hollowed out a comet, filled it with data storage, and sent it drifting through space, waiting to be discovered, waiting to be decoded. A seed ship. Perhaps BB is a terraforming vessel filled with microorganisms, genetic material, technology sent to colonize new systems. It drifts, waits, and when it encounters a suitable star, it activates, releases its payload, begins the slow process of seeding life. These ideas are fun, imaginative, but they are not science. They are science fiction, and there is a reason. Because every one of these scenarios requires assumptions that are not supported by data. BB's spectroscopy shows normal cometary molecules, CO, water, organics, no exotic compounds, no artificial emissions, no radio signals, nothing that screams engineered. Scientists test artificial hypotheses all the time. They model light curves, compare thermal emissions, analyze rotation rates, and every test comes back negative. BB behaves like a natural object. A weird natural object, yes, but natural. yet the whispers persist. And there is a reason for that. Because humans are pattern-seeking creatures. We want meaning, we want agency, we want to believe we are not alone. And when we see something unusual, something that does not fit our models, part of us wonders, could this be it? Could this be the sign we have been waiting for? The answer almost certainly is no. But the question itself is valuable because it forces us to think carefully about what we mean by natural, what we mean by artificial, and what we would look for if we really wanted to find evidence of extraterrestrial engineering. And so far, BB does not fit the profile. But here is the uncomfortable truth. If an advanced civilization did want to send something through our solar system, disguising it as a comet would be brilliant. It would move slowly, naturally, unthreateningly. We would assume it was ours, we would study it, and by the time we realize what it would be too late, or too far, or too strange to comprehend. That is the nightmare scenario, and it is almost certainly not happening. But almost is doing a lot of work in that sentence because we do not know, not for sure. And we will not know until we get close, until we send a probe, until we see BB up close and confirm definitively that it is just a comet, just a natural object, just a relic from the early solar system. But sending a probe, that is the problem because getting to BB is nearly impossible. Part 10. Mission Impossible. Why touching BB is nearly off the table. Space missions are hard. Really hard. Getting a spacecraft from Earth to another planet requires precise calculations, enormous energy, and years of planning. But getting to BB, that is on another level entirely. Because BB is not just distant, it is on a perpendicular orbit, and changing a spacecraft's inclination by 95 degrees, that is one of the most expensive maneuvers in orbital mechanics. Let us talk delta V. That is the term for the change in velocity a spacecraft needs to accomplish a mission. More delta V means more fuel. More fuel means more mass. More mass means bigger rockets. And bigger rockets mean bigger budgets. For reference, getting to Mars requires about 6 kilometers per second of delta phi. Getting to Jupiter, about 9. Getting to BB with its extreme inclination, easily 15 or more, maybe 20. That is in the realm of outer solar system missions like New Horizons, except harder. There is really only one plausible mission architecture, a Jupiter gravity assist. Launch a spacecraft toward Jupiter. Use Jupiter's massive gravity to bend the trajectory, change the inclination, redirect toward BB's orbital plane, and then cruise for years, decades maybe, until you intercept BB at some distant point in space. The launch window would be tight, probably somewhere between 2030 and 2034. After that, the geometry does not work. Jupiter will not be in the right position. BB will have moved. You would have to wait for the next alignment, which could be decades away. So if we are going to do this, we need to decide soon. Like really soon. But there are problems, big ones. First, power. At 11 astronomical units, where BB will be near perihelion, solar panels are almost useless. You need nuclear power, a radioisotope thermoelectric generator, RTG. But RTGs are expensive, politically sensitive, limited in supply. NASA has a few, but they are allocated to flagship missions, not speculative comet flybys. Second, communication. At 11 astronomical units, radio signals take over an hour to reach Earth. That is an hour each way, 2-hour round trip. You cannot fly a spacecraft in real time at that distance. Everything has to be autonomous, pre-programmed, and if something goes wrong, you cannot fix it. You just watch and hope. Third, navigation. BB is outgassing. That creates a coma, dust, gas, and all of that scatters light. Makes it hard to see the nucleus, hard to navigate precisely. A flyby mission needs to get within hundreds of kilometers to get good data. Miss by a few degrees, and you have wasted billions of dollars on fuzzy long-distance photos. Fourth, thermal control. BB is cold, really cold, and the spacecraft needs to survive that cold while also dealing with occasional heating from its own electronics. Thermal management in deep space is tricky. Engineers have solutions, but they add mass, complexity, cost. Most mission planners look at these challenges and walk away. The risk is too high. The cost is too high. And the scientific return, while interesting, does not justify the investment. You could launch 3 Mars missions for the cost of 1 BB flyby. And Mars gives you more science per dollar. But there is a small group of mission designers who will not give up. They have been quietly drafting a concept. A lightweight probe, minimal instruments, maybe just a camera and a spectrometer launched as a rideshare. Piggybacking on another mission to reduce costs. It would not orbit BB. It would not land. Just a fast flyby. Snap some pictures, grab some spectra, and send the data home. This ghost mission, as some call it, has never been officially proposed. It exists only in PowerPoint presentations and back-of-the-envelope calculations. But the idea is there, and if funding appeared, if political will aligned, it could happen. Barely, just barely. There is also hope in future technology. Solar sails, nuclear electric propulsion, advanced ion drives. These technologies could change the equation, make high delta-V missions more feasible, more affordable. But they are not ready yet. Not proven, not flight tested. And by the time they are, BB will be gone. So we are stuck. We have a unique ancient object approaching. An object that could tell us how the solar system formed, how dwarf planets evolved, how the Oort Cloud works. And we might never touch it, never study it up close. We will watch from a distance, take pictures, analyze spectra, and hope we are not missing something crucial. And that emotional tension, that frustration is real. Because science is not just about knowledge. It is about curiosity, about pushing boundaries, about reaching out and touching the unknown. And when we cannot, when the universe puts something just out of reach, it hurts. It reminds us how small we are, how limited, how trapped on this one pale blue dot. But here is the thing. Even if we cannot send a probe, we are still learning. Earth-based telescopes are incredibly powerful. Hubble, ALMA, the new James Webb Space Telescope. These instruments can see things we never thought possible. They can analyze atmospheres on distant planets, map molecular clouds in other galaxies, and they can study BB, watch it evolve, track its jets, measure its composition, and piece together its story. So maybe we do not need a mission. Maybe we already have what we need. Maybe the real breakthrough is not touching BB. It is understanding it from here, from home, using the tools we have. And maybe that is enough. Or maybe it is not. Maybe there is something on BB's surface, something in its interior that we will never see from Earth. Some crucial piece of the puzzle that requires hands-on study. And we will never know because we did not go. Because we chose safe, predictable missions over risky, ambitious ones. And future generations will look back and wonder, why did they not try? That is the weight of this moment, the responsibility. Because BB is coming, and whether we study it up close or from afar, whether we understand it or not, it is going to change how we think about the outer solar system, how we think about comets, how we think about what is possible out there in the dark. And the real question is not whether we can get there. It is whether we have the courage to try. Part 11. The 2025 Breakthrough in Dark Matter Mapping. The universe is mostly invisible. That is not poetry. That is physics. Roughly 85% of all matter in the universe is dark matter. We cannot see it, cannot touch it, cannot detect it directly. We only know it exists because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters are too massive. Something invisible is pulling strings. And we call that something dark matter. For decades, we have assumed dark matter is smooth, a diffuse halo surrounding galaxies, gentle, uniform. But in 2025, that assumption started to crack. New gravitational lensing studies combining data from multiple surveys revealed something unexpected. Dark matter is not smooth. It is granular, clumpy, lumpy, and those lumps might be smaller and denser than anyone predicted. Let me explain gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light. Einstein predicted this. We have confirmed it thousands of times. And by analyzing how light bends, we can map the distribution of mass, including invisible mass, including dark matter. The 2025 breakthrough came from a team analyzing data from the Euclid Space Telescope and ground-based surveys. They reconstructed the dark matter distribution in the local universe with unprecedented resolution. And what they found was shocking. Instead of a smooth halo, they saw structure, filaments, nodes, concentrations of dark matter far denser than expected on scales of just a few light years. Now, here is where it gets interesting for BB, because the Oort Cloud sits at the edge of the solar system, roughly 1 light-year out. And if dark matter clumps exist on light-year scales, they could pass through or near the Oort Cloud. And when they do, they exert gravity. Weak gravity, yes. But over millions of years, weak gravity adds up. Could dark matter clumps be perturbing Oort Cloud objects? Could they be the unseen forces nudging giants like BB inward? It is speculative, wildly speculative, but it is not impossible. Here is the problem. Dark matter interacts only through gravity. It does not collide, does not scatter, just pulls. And individual dark matter particles have tiny mass. Even a clump of dark matter would have relatively weak gravitational influence compared to, say, a planet or a passing star. So could it really affect comet orbits? The math is tricky. Some cosmologists say yes. If dark matter clumps are dense enough, massive enough, and pass close enough, they could perturb distant objects. Others say no. The effects would be too small, too diffuse, lost in the noise of other gravitational influences. But there is a story. A cosmologist, after running simulations with the new granular dark matter models, told their team something unsettling. If I am right, I just handed Oort Cloud theorists a wild card. Because if dark matter can clump this densely, we need to rethink everything we know about outer solar system dynamics. Every perturbation calculation, every comet trajectory, everything. The implications are enormous. If dark matter shapes comet orbits, then predicting future inbound objects becomes vastly more complicated. Because dark matter is invisible, we cannot track it. We cannot predict its movements. It is a random, unseen influence. Like trying to predict billiard ball trajectories when invisible hands are randomly tapping the table. This ties back to BB, because BB's orbit, its timing, its unusual inclination, all these might be influenced by dark matter. Maybe BB is not responding to a hidden planet. Maybe it is responding to a dark matter structure that passed through the Oort Cloud 10 million years ago, set it on this trajectory, and then moved on, leaving no trace except the object itself. Future research will test this, combining cosmology and solar system dynamics, modeling how dark matter clumps evolve over time, where they go, how often they Interact with the Oort Cloud, it is interdisciplinary, ambitious, and it might rewrite how we think about comet injection rates. But here is the existential question. If dark matter shapes our solar system, if invisible structures dictate which comets fall inward and which do not, what does that say about our place in the universe? It says we are more connected than we thought, that cosmic scale structures influence local events, that the Milky Way's dark matter halo is not just background, it is active, dynamic, shaping our neighborhood in ways we are only beginning to understand. And if that is true, then studying BB is not just solar system science, it is cosmology. It is a window into how dark matter works, how it clumps, how it interacts. And that makes BB even more valuable, even more mysterious, even more important. From the invisible pull of dark matter, we turn now to another cosmic mystery, one closer to home, but equally strange: the tilt of our solar system. Part 12. The solar system's tilt mystery reopened. Our solar system is crooked. The sun spins. It has an equator, and that equator is tilted about 6 degrees relative to the plane where the planets orbit. That might not sound like much, 6 degrees. But it is weird, really weird. Because the solar system formed from a rotating disk of gas and dust. Everything should be aligned. The sun's equator and the planetary orbits should match. But they do not. This has puzzled astronomers for decades. How did the sun get tilted? Was it always like this, or did something knock it off axis? And if something knocked it off axis, what was it? In 2025, new research combining data from NASA's Juno mission to Jupiter and the European Space Agency's Gaia star catalog reopened this mystery. Juno measured Jupiter's gravitational field with incredible precision. Gaia mapped stellar motions across the galaxy, and together these datasets allowed researchers to reconstruct the early dynamical history of the solar system with new accuracy. What they found was surprising. The tilt probably did not come from the solar system's formation. It came later from an external encounter. Maybe a passing star. Maybe a rogue planet. Something massive came close, exerted a gravitational torque, and tilted the young sun relative to the planetary disk. This matters because if that happened, if the solar system experienced a close encounter early in its history, that encounter would also have affected the Oort Cloud massively. It would have scattered objects, perturbed orbits, created the high inclination population we see today. And maybe, just maybe, it set BB on its current path. Think about it. If a massive object passed through the outer solar system 4 billion years ago, it could have simultaneously tilted the sun and destabilized BB's orbit. Two effects, one cause, and BB has been falling inward ever since, slowly over billions of years until now. Let me explain what we mean by gravitational torque. When a massive object passes near a rotating body, it doesn't just pull uniformly. It pulls harder on the near side than the far side. That differential force creates a twist, a torque. And if the torque is strong enough, it can change the rotation axis, tilt it, reorient it. This happens all the time in the universe. Moons get tidally locked to their planets. Binary stars affect each other's spins. It is basic celestial mechanics. But applying it to the sun is tricky. The sun is massive, really massive. It takes an enormous force to change its rotation axis. So whatever passed by must have been huge and close. Really close, probably within a few hundred astronomical units, maybe even closer. That is uncomfortably close for a young planetary system still forming. The Juno data is crucial here. Juno spent years orbiting Jupiter, mapping its gravitational field in exquisite detail. And buried in that data are clues about Jupiter's formation and early evolution, how it migrated, how it interacted with other planets, how the entire solar system's architecture came to be. And when you combine that with Gaia's stellar motion data, which shows how nearby stars have moved over millions of years, you can work backwards, reconstruct ancient encounters, figure out who might have visited. The leading candidate is a star, not our sun's binary companion. We do not think the sun ever had one that close, but a star from the same stellar nursery. When the sun formed, it was not alone. It was part of a cluster. Hundreds, maybe thousands of young stars, all born from the same molecular cloud. And in those early days, stars were packed close, much closer than they are now. Encounters were common, almost inevitable. So picture this. 4 billion years ago, give or take, a young star passes within a few hundred astronomical units of the sun, close enough that its gravity reaches inward, pulls on the outer planets, tugs on the sun's outer layers, creates enormous tidal stresses, and over the course of the encounter, which might have lasted thousands of years, the sun's rotation axis shifts. 6 degrees, not catastrophic, not enough to disrupt the planets, but enough to notice, enough to matter. Alternative ideas exist. Some researchers propose internal angular momentum evolution. The idea that the sun's rotation slowed over time due to magnetic braking and that somehow created the tilt. The sun has a magnetic field. That field interacts with the solar wind. The stream of particles flowing outward from the sun, and that interaction acts like a brake, slowing the sun's rotation over millions of years. But here is the problem. Magnetic braking slows rotation. It does not tilt it. You would need some asymmetry, some uneven distribution of mass or magnetic field, and there is no evidence for that. The sun appears remarkably symmetric, so while magnetic braking is real, it probably does not explain the tilt. Others suggest asymmetries in the protoplanetary disk. Gas flowing in uneven patterns, creating torques, nudging the sun. This could work in principle, if the disk had large-scale turbulence, or if gas was falling in from a preferred direction, it could create enough torque to tilt the sun. But again, there is no direct evidence, and the disk would have to be unusually asymmetric, more asymmetric than simulations typically produce. But these explanations feel weak. They require fine-tuning, special conditions. The passing encounter hypothesis is simpler, more robust. One big event explains multiple mysteries. A planetary scientist ran Monte Carlo simulations, thousands of them, modeling different encounter scenarios, different masses, different velocities, different trajectories, and only a narrow set of encounters produced both the solar system's tilt and the orbital distribution of Oort Cloud objects, including BB's perpendicular orbit. That is not proof. It is correlation, but it is suggestive, and it hints at something profound. Our solar system did not evolve in isolation. It had visitors, interactions, close calls, and those events shaped everything. The sun's tilt, the Oort Cloud structure, the comets we see today. The simulations are fascinating. You set up a young solar system, planets still migrating, Oort Cloud still forming, and then you throw in a passing star, vary its mass, its velocity, its trajectory, and watch what happens. Most encounters do nothing interesting. The star passes too far. Its influence is negligible. But occasionally you get the right combination. The star passes at just the right distance, just the right speed. And suddenly everything changes. The sun tilts. The outer planet's orbits shift slightly, and the Oort Cloud goes crazy. Objects get scattered. Some fall inward. Some get ejected entirely. and the ones that remain end up on weird orbits, high inclinations, extreme eccentricities, perpendicular paths, just like BB. And if one encounter happened 4 billion years ago, could others have happened more recently? Could there be a pattern of encounters, a rhythm, a cosmic drumbeat of passing objects that periodically disturb the outer solar system? Some dynamicists think so. They propose that stellar encounters happen roughly every 100 million years. Not exact, not predictable, but common enough to matter. And each encounter sends a new wave of comets inward, creating pulses of activity, clusters of unusual objects. The evidence for this comes from comet statistics. When you look at the arrival rate of long-period comets, objects from the Oort Cloud, it is not constant. It varies. And some researchers claim to see periodicities, cycles, peaks, and valleys in the arrival rate, separated by tens of millions of years. Others are skeptical. They argue the signal is too noisy, too uncertain. But the idea persists. If that is true, then BB is part of a pulse, a wave, and there are others already on their way. We just have not seen them yet. And that is both exciting and terrifying, because it means the outer solar system is more dynamic than we thought, more active, more dangerous. But here is the really unsettling part. If stellar encounters shaped the Oort Cloud, if they are responsible for sending comets inward, then predicting future arrivals becomes nearly impossible. Because we cannot predict stellar encounters, stars move chaotically. Gravitational interactions with the galaxy are complex. There is no simple formula, no way to say the next encounter will happen in X million years. It is random, stochastic, unpredictable. That means we cannot forecast future BB-like objects with certainty. We can estimate probabilities. We can say statistically we expect one giant comet every million years, but we cannot say when. We cannot say from which direction. We can only watch and hope we have enough warning. But understanding the tilt is not just about comets. It is about origins, about how planetary systems form and evolve, about whether our solar system is typical or unusual. And right now, we do not know. We need more data, more simulations, more observations of other star systems to compare. The good news is we are starting to get that data. Telescopes like ALMA and the James Webb Space Telescope are imaging protoplanetary disks around young stars, watching planets form in real time, and what they are seeing is surprising. Many of these disks are tilted, warped, asymmetric, just like we think our early solar system might have been. So maybe we are not unusual. Maybe stellar encounters and tilted disks are common. Maybe every planetary system goes through this. Or maybe we are special. Maybe most systems evolve in isolation, and we got unlucky or lucky depending on your perspective. Because that ancient encounter, the one that tilted the sun and scattered the Oort Cloud, might have been essential for life on Earth. Maybe it cleared out dangerous debris. Maybe it prevented a later catastrophic impact. Maybe we owe our existence to that cosmic near miss. We do not know. We may never know for certain. But the pieces are coming together. The Juno data, the Gaia catalog, the simulations, the observations of other star systems. All of it points toward a solar system shaped by encounters, by external forces, by a history more violent and chaotic than we once believed. And BB is part of that history. A survivor, a relic from an encounter that happened billions of years ago, an object sent on a slow journey inward, carrying with it the memory of ancient violence. And now, finally, after all this time, it is arriving, coming home, or perhaps coming to tell us something we need to know about where we came from. about how fragile our existence is, about how the cosmos shapes everything, even down to the tilt of our own sun. And speaking of cosmic mysteries, there is another one. Larger, stranger, more fundamental, a hole in the universe itself. And recent observations suggest it is deeper than we thought. Part 13. The supervoid anomaly gets stranger. The universe, when viewed at the larger scales, is not uniform. It is a cosmic web. Filaments of galaxies separated by vast voids, regions where almost nothing exists, empty space stretching for billions of light years. And one of these voids is particularly strange. It is called the cold spot. The cold spot appears in the cosmic microwave background, the CMB. That is the afterglow of the Big Bang. Light from the early universe stretched and cooled over 14 billion years. The CMB is remarkably uniform. Temperature variations are tiny, a few parts in 100,000. But there is one region that is colder than it should be, significantly colder, and astronomers have been arguing about it for 20 years. In 2025, a team reanalyzed CMB data from the Planck satellite and new ground-based surveys. They used improved statistical methods, better noise filtering, and what they found was unsettling. The cold spot is deeper than previous models suggested, more extreme, more significant. Why does this matter? Because the cold spot might be linked to a supervoid, an enormous region of space with much lower density than average. And if you look through a supervoid, light from the CMB loses energy. It cools, creates a cold spot. That is the theory, but the numbers do not quite work. The supervoid needed to explain the cold spot would have to be enormous. Unusually enormous, uncomfortably enormous. Let me break down what we are talking about. The supervoid is not just empty space. Space is already mostly empty. A supervoid is a region where even galaxies are scarce, where the average density of matter is significantly lower than the cosmic mean. And these voids can be huge, hundreds of millions of light years across, maybe a billion light years. That is bigger than galaxy clusters, bigger than superclusters. It is structure at the absolute largest scales the universe allows. When CMB photons, those ancient particles of light from the Big Bang, travel through a supervoid, something strange happens. They fall into the gravitational well of the void. As they fall, they gain energy, blue shift. But then, as they climb out the other side, they should lose that energy, red shift. Normally, these effects cancel out. But if the universe is expanding, and it is, the void grows while the photon is passing through it. So the photon does not climb out of quite the same gravitational well it fell into. It loses slightly more energy than it gained. Ends up slightly cooler. That is called the integrated Sachs-Wolf effect. And it is real. We have measured it. But here is the problem. The cold spot is too cold, too big. The supervoid needed to create it using standard physics would have to be implausibly large, implausibly empty, on the edge of statistical impossibility. Not actually impossible, just really, really unlikely. And that makes astronomers nervous. Some cosmologists now wonder if the cold spot is evidence of something more exotic. Maybe it is a window, a glimpse into alternate physics. Or maybe it is a scar, a mark left by colliding universe bubbles in a multiverse. Or maybe it is just statistical noise, a fluke, one in a million chance, and we are reading too much into it. The multiverse idea is particularly provocative. Some theories of cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, suggest that our universe is just one bubble in an infinite foam of universes. Each bubble has its own laws of physics, its own constants, its own properties, and occasionally these bubbles collide. When they do, they leave marks, scars in the fabric of space-time. And maybe, just maybe, the cold spot is one of those scars. The math works, sort of. Models of colliding universe bubbles predict cold spots in the CMB, but they also predict other features, specific patterns in the temperature fluctuations, specific statistical signatures, and so far, those have not been conclusively detected. So the multiverse explanation remains speculative, tantalizing, but unproven. Then there is the exotic physics angle. What if the cold spot reveals something about dark energy? Dark energy is the mysterious force driving the universe's accelerating expansion. We know it exists. We can measure its effects, but we do not know what it is. And some theorists propose that dark energy is not uniform, that it varies from place to place. And maybe the supervoid is a region where dark energy is slightly different, where the expansion rate is slightly faster, and that creates the cold spot. Again, the math kind of works, but there is no independent evidence, no other observations that support variable dark energy. So it remains a possibility, not a leading theory, just one option among many. But here is the speculative leap. If the cold spot is real, if it represents an actual anomaly in the universe's structure, could it affect local dynamics? Could gravitational effects from such a large-scale structure influence the Oort cloud? Could BB be responding, however indirectly, to the universe's largest voids and filaments? It sounds absurd. The cold spot is billions of light-years away. BB is here in our solar system. How could they possibly be connected? But gravity does not care about distance. It is infinite range. Weak at large scales, yes, but cumulative. And maybe, just maybe, the universe's structure creates subtle tidal forces that percolate down to small scales, affecting galaxies, affecting stars, affecting Oort clouds. Think about it this way. We know galactic tides affect the Oort cloud. The combined gravitational pull of the Milky Way's disk and bulge creates tidal forces that perturb distant comets. Those forces are tiny, but they are real, and they accumulate over millions of years. So, what about larger structures? What about the pull from nearby galaxy clusters, from cosmic filaments, from supervoids? The calculations are brutal. You are dealing with forces so weak they are almost negligible. Almost, but not quite. Some dynamicists have run simulations, modeled how external gravitational influences from large-scale structure might affect Oort cloud dynamics. And the answer is maybe. It is possible. The effects are small, but over billions of years, small effects can produce noticeable changes in orbital distributions. If the cold spot represents a supervoid, and if that supervoid is relatively nearby in cosmic terms, maybe a few billion light-years, then its gravitational influence could subtly shape the orbits of the most distant Oort cloud objects. Not dramatically, not enough to send them plummeting inward on their own, but enough to nudge them, perturb them, make them slightly more susceptible to other influences. And maybe BB is one of those objects. Maybe its orbit was shaped in part by the gravitational pull of cosmic voids and filaments. Maybe the reason it is falling inward now is because billions of years ago, the universe's large-scale structure gave it a tiny push. And that push, combined with galactic tides and stellar encounters and everything else, eventually centered on its current trajectory. This is highly speculative. Wildly so. Most astronomers would dismiss it outright. The effects are too small, too diffuse, too uncertain. But a few are intrigued because if it is true, if cosmic scale structure really does influence local dynamics, then we need to completely rethink how we model the Oort cloud, how we predict comet arrivals, how we understand the architecture of the outer solar system. A cosmologist, after reviewing the new cold spot data, joked with colleagues, "If the cold spot is a window, what is on the other side?" It was a joke, but it is also a real question, because if our universe is part of a multiverse, if other universes exist, then maybe the cold spot is where they touch, where the membranes meet, and maybe that has consequences. Imagine standing at the boundary between two universes. What would that even mean? The laws of physics might be different. The constants might vary. Time itself might flow differently. And if our universe is touching another one, if they are in contact, even briefly in cosmic terms, then energy could flow, information could leak, gravitational effects could propagate. And maybe, just maybe, some of those effects reach us, reach the Milky Way, reach the solar system, reach the Oort Cloud. It is the ultimate cosmic connection. The idea that an object in our solar system, a comet falling toward the sun, might be influenced by forces originating in another universe entirely, it is almost too strange to contemplate. But that is the nature of modern cosmology. We have pushed our understanding so far, explored scales so vast that the boundaries between science and science fiction blur. But speculation drives science. It pushes boundaries. It asks uncomfortable questions. And sometimes, rarely, speculation turns out to be right. And if there is even a tiny chance that cosmic scale structure influences comet dynamics, we need to explore it, because understanding BB means understanding everything from the smallest ice grain to the largest cosmic voids. The cold spot might turn out to be nothing, a statistical fluke, a quirk of measurement, a reminder that even the most careful observations can mislead. But it might also be something profound, a window into physics we do not yet understand, a connection between scales we thought were separate, a hint that the universe is even stranger than we dared imagine. And if BB is part of that strangeness, if its journey toward the sun is shaped by forces operating at the largest scales imaginable, then studying BB becomes more than just solar system science. It becomes cosmology. It becomes a test of how the universe works at every level, from the quantum to the cosmic, from the local to the universal. That is the power of anomalies, of objects that do not quite fit, of cold spots and giant comets and perpendicular orbits. They force us to question, to investigate, to connect dots we thought were unconnected. And sometimes in that process, we discover that the universe is far more interconnected than we ever realized, that nothing exists in isolation, that everything from the smallest particle to the largest void is part of a single, incomprehensibly complex system. And that understanding is changing because we have new tools, new methods, new ways of modeling the universe. And one of those new tools is artificial intelligence, and it is already revealing things we never expected. Part 14. The AI that models the universe better than humans expected. Simulations are the backbone of modern astrophysics. We cannot experiment on galaxies, cannot rerun the formation of the solar system. So, we simulate. We build computer models, feed in physics, let the code evolve, and see what emerges. But simulations are expensive, computationally brutal. Modeling the entire Oort Cloud, every object, every interaction, every perturbation would take centuries on current supercomputers. Enter artificial intelligence. In 2025, a team unveiled a breakthrough, a neural network trained on hybrid cosmology and gravitational data. It can predict large-scale structure formation more accurately than traditional N-body simulations. And it does it 100 times faster, maybe 1,000 times faster. This is revolutionary because suddenly simulations that were impossible are now feasible. We can model the Oort Cloud in exquisite detail, track individual objects over billions of years, test perturbation scenarios, and see which ones match observations. The AI works by learning patterns. It does not solve equations step by step. It learns from data, from previous simulations, from observations, and it finds shortcuts, emergent patterns humans missed. It is not magic. It is just pattern recognition at scale. But it is incredibly powerful. Researchers have started feeding it solar system data, known comet orbits, planetary positions, and they are asking it to predict where the next giant comet will come from, what its orbit will be, when it will arrive, and the results are stunning. The AI flags perturbation signatures human modelers did not prioritize. It suggests hidden influences, forces we have not fully accounted for. For example, the AI noticed a correlation between BB's orbital parameters and the distribution of distant TNOs. A correlation so subtle that statistical tests barely detect it. But the AI insists it is real. And when researchers dug deeper, they found it might be linked to a past gravitational interaction, something we had missed. This is the power of AI. It sees patterns we cannot. But there is a danger. AI models are only as good as their training data. If the data is biased, incomplete, or wrong, the AI will learn those errors, amplify them, and produce garbage predictions dressed up as breakthroughs. So scientists are cautious. They test AI predictions against observations. They compare different models. They demand reproducibility, and they never trust AI blindly. It is a tool, a powerful tool, but still just a tool. There is a story. A computational astrophysicist spent 6 months training an AI on 50 years of comet observation data, orbital mechanics, brightness curves, spectroscopy, everything available. And then they asked it a simple question. Where will the next BB-sized object come from? The AI thought for hours, processing, calculating, and then it spat out coordinates, a specific region of the Oort Cloud, a specific time frame, 20 to 30 years from now. The astrophysicist was skeptical. They checked the math, ran independent simulations, and everything supported the AI's prediction. But here is the uncomfortable part. The AI also flagged secondary predictions, things it noticed but could not explain, anomalies in the data, perturbations that did not match known physics. And when pressed, when asked to justify these anomalies, the AI could not. It just said, "The pattern is there." That is both exciting and terrifying, because it means the AI might be seeing real effects we do not understand yet. Or it might be hallucinating patterns from noise, finding faces in clouds, and we will not know which until the future arrives, and we can check its predictions. But the potential is enormous. Imagine combining observational campaigns, Hubble, ALMA, ground-based surveys with AI-driven predictive models. We could forecast comet arrivals decades in advance, identify dangerous objects before they get close, plan missions with confidence. It would transform how we study the outer solar system. And for BB specifically, AI could help us understand its evolution, how its jets will change as it approaches perihelion, whether it will fragment, what its composition reveals about solar system formation. We could run thousands of scenarios, test every hypothesis, and converge on the truth faster than ever before. But there is a philosophical question lurking here. If an AI tells us something we do not understand, something that contradicts our models, should we believe it? Should we trust a black box? Or should we demand human understandable explanations for every prediction? Different scientists have different answers. Some embrace AI fully. They argue that human intuition is limited, biased, evolved for survival on Earth, not for understanding cosmic mechanics. AI does not have those limitations. It can see patterns we are blind to, so trust it. Others are cautious. They argue that science requires understanding, not just prediction. A model that predicts correctly but cannot explain why is alchemy, not physics. We need transparency, interpretability, human comprehension. Both sides have merit, and the debate will shape the future of astronomy. But for now, AI is here. It is being used, and it is changing how we study objects like BB, whether we fully understand it or not. The implications extend beyond just prediction. The AI is also revealing something deeper about how we have been thinking about the Oort Cloud. For decades, we have modeled it as a relatively static reservoir. Objects sit out there waiting. Occasionally, something perturbs them, and they fall inward. Simple, clean. But the AI suggests something more dynamic, something more chaotic. When researchers fed the AI data on known long-period comets, objects that came from the Oort Cloud in the past, the AI started detecting patterns in their arrival times. Not random, not quite periodic, but structured like waves, pulses of activity separated by millions of years, as if something keeps disturbing the Oort Cloud in cycles. This matches some theoretical work from the 1980s and 90s. Ideas about galactic tides creating periodic comet showers. But those ideas fell out of favor. The data was too noisy, the evidence too weak. But now the AI, processing vastly more data with far more sophisticated algorithms, is resurrecting those ideas, suggesting they might have been right all along. And if comet arrivals come in pulses, if BB is part of a wave, then we need to rethink our entire approach to planetary defense. Because it is not just about tracking individual objects, it is about understanding the cycles, predicting when the next pulse will arrive, preparing for multiple large objects, not just one. The AI has also started making predictions about the Oort Cloud structure. Traditional models assume it is roughly spherical, a uniform shell surrounding the solar system. But the AI suggests asymmetries, regions where the density is higher, clumps, voids, structure that reflects the solar system's journey through the galaxy over billions of years. Some of these predicted structures align with known features, the scattered disk, the inner cloud, but others are new. The AI predicts a concentration of objects in a specific direction toward the constellation Perseus. Why? Nobody knows. But if it is right, if we point our telescopes that direction and start finding more objects, then the AI just revealed something fundamental about solar system architecture. There is resistance, of course. Some astronomers argue we are putting too much faith in machine learning, that we are letting algorithms drive research instead of human insight, that we are becoming passive observers waiting for AI to tell us what to think. And there is truth to that concern. Science should not be outsourced to black boxes. Human creativity, intuition, skepticism. These are essential. They are what separates science from mere data processing. But others counter that AI is not replacing human scientists. It is augmenting them, doing the tedious work of pattern recognition so humans can focus on interpretation, on asking why, on designing experiments, on building theories. The AI sees the patterns. Humans give them meaning. Together, they are more powerful than either alone. And for objects like BB, that partnership is crucial because BB is complicated, multifaceted. It is not just an orbital problem or a composition problem or a perturbation problem. It is all of those simultaneously. And the only way to solve problems that complex is to throw every tool we have at them, including AI. The future of Oort Cloud research, the future of comet science increasingly depends on these AI models. They are becoming indispensable. And as they improve, as they ingest more data and refine their algorithms, they will only get better, more accurate, more insightful, more unsettling in what they reveal. Because that is the pattern. Every new tool, every new method reveals that the universe is stranger than we thought. Telescopes showed us distant galaxies. Spectroscopy showed us what they are made of. Computer simulations showed us how they evolved. And now AI is showing us patterns we never suspected, structures we never imagined, possibilities we never considered. BB is part of that revelation. A single object, a single comet. But it is teaching us that the outer solar system is more complex, more dynamic, more mysterious than we ever realized. And the AI is helping us see that, helping us understand, even if we do not fully understand the AI itself. And speaking of things we do not fully understand, there is one more cosmic mystery, one that strikes at the very foundations of physics, a theory that emerged in 2025 and sent ripples through physics departments worldwide. A theory that suggests our most basic assumptions about how objects move might be wrong. Part 15. The New Physics Rumor Mill, 2025's most controversial paper. In 2025, a paper circulated, not through major journals at first, through preprint servers, email chains, quiet, conversations at conferences, and it proposed something radical, something that most physicists dismissed immediately. But a few, a small but growing few, found it impossible to ignore. The paper suggested that inertia, the resistance of mass to acceleration, might not be constant, might vary depending on cosmic environment. Specifically, it proposed that inertia changes at galactic scales out in the deep dark between stars in the outer reaches of planetary systems, where gravitational fields are weak and matter is sparse. In those regions, the paper argued mass behaves differently, not dramatically, but measurably. The motivation behind this theory is frustration. Dark matter explains a lot: galactic rotation curves, gravitational lensing, large-scale structure, but it does not explain everything. There are anomalies, small discrepancies, weird behaviors at the edges of galaxies. And some physicists wonder if maybe, just maybe, we are missing something more fundamental than invisible matter. What if inertia itself is wrong? What if Newton's laws, refined by Einstein, are still incomplete? What if there is another layer beneath general relativity that we have not discovered yet? The paper proposes a modification, a subtle one. At normal scales near planets and stars, the modification is negligible. Physics works as expected. But at extreme distances, in the Oort Cloud, for example, inertia increases slightly. Mass resists acceleration more than Newton predicts. And over millions of years, this changes trajectories, changes orbits, creates deviations. If this theory is correct, even partially, it could explain BB's orbit without invoking hidden planets or dark matter clumps. Because if inertia is different in the Oort Cloud, then objects there evolve differently. Their paths deviate subtly from Newtonian predictions, and over billions of years those deviations add up, create high inclination orbits, create anomalies, create objects like BB. The criticism was immediate. The math is elegant, many physicists said. But where is the empirical evidence? How do you test this? How do you measure inertia at those scales? And even if you could, Would we not have noticed discrepancies by now? Would spacecraft trajectories not show anomalies? The author, a young theoretical physicist, argued that we have noticed anomalies exist. Pioneer anomaly, anomalous accelerations in deep space probes, unexplained trajectory deviations. Most have been explained away. Thermal effects, outgassing, modeling errors. But maybe some are real. Maybe they are hints of variable inertia. The paper was submitted to major journals. Rejected, resubmitted, rejected again. One reviewer wrote, "This is mathematically interesting but physically speculative. Come back with data." Another wrote, "If you are right, you have just overturned 3 centuries of physics. Extraordinary claims require extraordinary evidence." But the paper found supporters. A small group of physicists who have been wrestling with galactic dynamics for decades, who have tried to make dark matter work and found it lacking, who are willing to consider alternatives, even radical ones. They do not fully endorse the theory, but they are intrigued. They are running simulations, testing predictions, looking for observational signatures. And here is where it ties to BB. If variable inertia is real, then every comet trajectory calculation we have ever done is slightly wrong. Not hugely wrong, not obviously wrong, but wrong enough to matter over billions of years. And objects like BB, which have spent eons in the Oort Cloud, where inertia is allegedly different, would show the effects most clearly. So studying BB becomes a test, a way to check if inertia really varies. If BB's orbit deviates from predictions in specific ways, ways consistent with variable inertia, that is evidence. Not proof, but evidence. And if enough objects show similar deviations, the theory gains credibility. There is a story. The physicist who wrote the paper received hate mail. Anonymous emails calling them a crank, a fraud, a disgrace to science. But they also received messages of support from researchers who had privately wondered the same things, who had seen the same anomalies and been too cautious to speak up. And one message said simply, "Keep going. You might be wrong, but you might be right. And if you are right, everything changes." That is the nature of revolutionary science. It is uncomfortable, divisive. Most revolutionary ideas are wrong, spectacularly wrong. But some are not. Some turn out to be glimpses of deeper truth. And we never know which is which until we test them, until we gather data, until we let reality decide. So what does this mean for BB? It means BB is not just a comet. It is a test case, a messenger. Whether it is revealing dark matter structures or variable inertia or hidden planets, or just standard comet physics scaled up, BB is teaching us something about the outer solar system, about cosmic forces, about the limits of our knowledge. And maybe that is the real story. Not that BB is unusual, but that it is forcing us to question everything, to re-examine assumptions, to consider possibilities we dismissed, to admit that despite centuries of astronomy, despite powerful telescopes and sophisticated models, we still do not understand the universe. Not fully, not even close. BB is heading toward the sun slowly, majestically, inevitably. And as it approaches, it carries with it mysteries, ancient ones, frozen in ice for billions of years, waiting to be revealed. And we are watching, studying, speculating, hoping to understand before it is too late, before it swings past perihelion and heads back into the darkness. But here is the uncomfortable truth. Even if we study BB perfectly, even if we map every jet, analyze every molecule, model every perturbation, even if we understand it completely, there will be others. More giants lurking in the Oort Cloud, more anomalies drifting inward, more mysteries waiting to challenge everything we think we know. Because the universe is not done surprising us. It never is. Every answer raises new questions. Every discovery reveals new ignorance. And objects like BB, objects that do not quite fit, that break our models, that force us to think differently, those are the most valuable of all, because they are the ones that teach us we were wrong. And being wrong, admitting it, fixing it, that is how science progresses. So, as BB continues its long fall toward the sun, as we watch and wait and wonder, remember this. This giant comet is not just a relic. It is a messenger of forces we barely understand, of physics we are still discovering, of a universe far stranger and more complex than we ever imagined. And if we listen, if we pay attention, if we are brave enough to question our assumptions and follow the evidence wherever it leads, then maybe, just maybe, BB will teach us something profound about where we came from, about what is out there, about how little we really know. And that thought, that humbling, exhilarating, terrifying thought, should keep us all looking up, searching the darkness, waiting for the next giant to emerge. Because they are out there somewhere, drifting in the cold, waiting for their turn, waiting to challenge us, to surprise us, to remind us that the universe is vast and strange and full of wonders we have not even begun to understand. The cosmic drumbeat continues, and we are only just learning to hear.